we talked a little bit about application from blast design all the way through analysis. And we're going to take it a little bit further here today. We're going to talk about utilizing drones for blast optimization and talk specifically about the tools that we used on a specific case study, and I'll give you the results on that study as well, and just kind of a good overview of the technology and the process and how this all kind of fits together to go in and optimize a blast operation, say for example in this case quarry operations. So with that, let's see here. Well, there we go. So as far as the tools for optimizing a program, first off, obviously we've got a capable drone that's required, and I'll talk a little bit more in detail about that. And along with that is surveying equipment. In most cases, GPS systems are probably the more preferred system that we see out in the field. And along with that, also borehole survey systems as well. The borehole survey system obviously allows us to track that hole, and then we can combine it with the face profile and get those minimum burdens. And for those of you that joined our last presentation, we got into quite a bit of detail about minimum burdens and how those are captured and how they're presented and how important and effective it is for the blaster to have that. Along with this, we're also going to talk about a very key component, and that's the software that's designed specifically for blast optimization, the design, the planning, the analysis, all the way through, and how this is really one of the key components of all this to be able to manage all of this and be able to go in and assess and optimize your blasts. So let's first start off with the drones, and there's really two primary platforms that we have out here today. One is our fixed wing, and the other is the rotorcraft. And here you can see an example of one of the fixed wing drones on the screen, and here's the rotorcraft. Now, I say these are the two primary platforms. I know that today there are some fixed wing units out there that have what's called VTOL capability. That's vertical takeoff and landing. But there's a big difference in the performance in the field with these. And what we found is that the rotorcraft, really, in our experience, has given us the capabilities that we need to be able to go in there and do a proper blast optimization program. And where the fixed wing just didn't quite cover all the capabilities that we need with that. But either way, with both those, some of the key things that you need is, one, a very good high quality camera, which typically a lot of your higher end drones that have or that come out today have these types of cameras with it. And along with that is a gimbal, so we can rotate that camera and be able to capture, the face or overhangs and things like that. So it's important that we have that capability, especially where we've got deviations in the face that we've got to capture and be able to show that. Along with this is also the flight software. And most drones, as they're purchased off the shelf, come with just kind of a minimal package so that it can be hand flown. In some cases where maybe you're doing some larger scale mapping, things along this line, the flight software is really beneficial to help out in those types of applications. So that may be something that you'd want to look at, depending, again, what is your goal in this and what type of flights are you planning to do, especially if we're looking at kind of large scale mapping, ortho, to generate an ortho map. That's where the flight software can come in pretty handy. But in a lot of cases, we find there's a fair amount of hand flying that's required to be able to go out there and really generate an accurate model that really depicts the characterization of that face. So again, it's something there that may also be needed depending on the, again, on the application that you have. Next, we'll talk a little bit about the drone surveys on the software side for blast optimization. And again, as we mentioned, having very specific software designed for design and analysis is critical, because we need that seamless data flow where we can go in there and bring data in this case, like from our drone, being able to bring the images in from our GPS. We're looking to export and import coordinates, our northings, eastings, elevations. The same with the drill. We can do our designs, export those coordinates out to the drill, and then once the drill's finished, import that back in, as well as measure while drilling and possibly other types of data that we might be able to generate off of these smart rigs. Along with that is being able to also generate the profiles. And again, the minimum burden profile is what we need to be able to design that shot correctly and be able to optimize that blast. So it's important that we're able to capture that face accurately and then be able to generate the design according to the characteristics of that face. And then the next part of that is the follow-up analysis, like we see here with fragmentation and muck pile configurations and things like that. And we'll talk a bit more in detail about those as well. So you can see here where, the blast design software is really a key component to be able to go in there and do proper optimization. This will give you an idea of the workflow, and this is very typical of a lot of operations we have in and around here in the US and across the country that are utilizing this technology on a day-to-day basis. We'll first start off with the GPS. In this case, you can see this is a portable system that we have here. It could be a permanent mount as well. Typically, a lot of your larger mining open pit operations may already have GPS running at those sites, but we find a lot of the smaller quarries don't have that capability. So in those cases, it's very convenient to be able to have a portable base station that we can bring into a site, set up on a hub, and be able to get accurate coordinate measurements for the site. The next part of the process is the flight. Typically, most off-the-shelf drones we're able to take out and fly our mission and capture that area of interest. And from that, we download those images into the software. And from there, we can generate the model. We can characterize the rock mass. We can do our blast design. And along with that, and most importantly as well, is we can then georeference that to whatever coordinate system. It could be a local coordinate system. It could be state plane or some sort of a area type coordinate system. Again, that's the key, because with our GPS, we can be assured that we can maintain that accuracy to be able to generate that and then get that model scaled accordingly. The next part of this is the actual blast design. And we reference this as a georeferenced as designed pattern. This is important because once we've generated this, this will be the basis that we'll look to implement into the field for drilling. So once this is generated, this would get passed on to the driller. The layout of this could be handled a couple ways. One, we could just upload the borehole coordinates to a GPS rover and go lay those out. Or if we have a smart drill, we could actually just email that over. They could load that up in there, and they would have the coordinate system loaded up in the drill. And now with these new smart drill, with the new smart drill technology that's out there with the drill navigation, they would be able to track right up to the collar as we've got it placed in our design. Once the drilling takes place, if they run into situations where They have to change the pattern. It could be water conditions. It could be they can't hold a hole in certain areas. A whole host of things may require changes in that pattern as they drill. In that case, that information is then archived and then transferred back into the software. And then at that point, they're able to generate what we call a georeferenced as drilled file. The nice thing about this is there's no need to go back out and reprofile the site. Once we have that model, it's just simply updating that. Along with the drill, we may have some borehole logs with that, where we've done a survey and bore track the hole. And that information, again, would also go in there and update that as drilled georeferenced file. So now we have the characterization of the face and the actual location and position of that drilled hole. So at that point, we're actually able to run, generate what we call a true minimum burden profile like we see here. And this is exactly what we need to be able to get the energy factor correct, or our powder factors, depending on what you're using, to be able to get that dialed in correctly. So you can see the workflow with this. Following the shot, then we can go in and do a post-blast analysis. And that may mean fragmentation. It could be muck pile configuration, cast throw, power trough, the whole host of things. But the nice part about that now in the software today, we can manage all of this with a seamless data flow all the way through, from collecting it to generating the as design, updating it to the as drilled, getting the blast, the reports out, the profile reports out for the blasters, and then following the shot, be able to follow up and generate the blast analysis information that we need to further optimize. The software today, it's come a long ways, especially with some of the better laptops that we have out. It's a very quick and very accurate survey that we can generate from that. Of course, the scaling and all is very critical in that process, but where we see the value of this is on the blast design side. We can now go in and generate patterns and designs for very complex blasts. So it may be, you could have a staggered pattern, square pattern, rectangular patterns, whatever it is. It may have a multitude of angle holes in it, whether certain areas, certain rows, corners, whatever the case may be. Even three-sided shots now can be managed in the software to be able to handle those types of complex designs. But again, the critical thing is we're generating this minimum burden profile. And as we mentioned earlier, this is important. It's really key that the blaster has this information to be able to load that accordingly for safety, to mitigate any kind of potential fly rack, also for mitigation air overpressure, and then obviously for control and performance of the shot as well. Along with that, the softwares today are smart drill compatible. Allows us to generate those designs. As we mentioned, send it to the drill. The drill is able to send back that as drilled file, and it can be updated. So now we can make good decisions on the bench on how to handle situations, especially where things change. And in the event that we've got pattern changes or things like that, this is where this becomes quite critical. On the blast analysis side, one of the key areas that we find as a tool to go in and analyze is muck pile configuration. We can look at the movement, swell, volumes. All these things can tell us a lot of good information about the performance of the shot. Here you can see where we've positioned a plane mid-blast. And you can see on the lower left, the pre-blast, and then there in the center, post-blast And on the right, you can see how we can overlay the profiles, the cross-sectional profiles on top of each other, so you can see pre and post in there, so we can get an idea of what that power trough looks like. We can also see how far that material is moved out. So in the event we're changing explosives, we're changing delay times, patterns, hole diameters, things like that, we can use this as a tool to be able to gauge what kind of performance that we're getting with that. And even in a situation we're doing progressive excavation and things like that, we'll talk a little bit more in detail about that here in a minute. But on this one, you can see here, we've got our pre-blast cross-section, post-blast cross-section, and then also mid and final excavations as well. So again, we can overlay those cross-sections right in there and be able to see what we're getting performance-wise. So now we've got a tool that allows us to compare to, say, our benchmarked shot and see if, in fact, we're heading the right direction with our performance. So it's a tremendous tool to use in that kind of a situation. Along with that is 3D fragmentation. And if any of you happen to catch the webinar we just had this last week on this, very unique to the industry. In the past, it's always been a 2D fragmentation, and it's always had its challenges because it needed scales. It had a difficult time determining fines versus solid materials. Well, now we've been able to overcome that with 3D fragmentation, because as we fly that muck pile, we don't have to introduce any scale onto the pile like in the past, which typically was a problem and even dangerous in some areas to be able to do that. Now we can just fly over the muck pile, capture it. We can then select areas that we want to look at to determine the size distribution and capture that again in 3D, because now we can see the defined particles in there and it captures it, and we can differentiate that from, say, areas where we've got fines and things like that. So this is a tremendous tool for optimizing to determine if we're heading the right direction, whether it's oversize reduction, attaining certain uniformity, or possibly trying to reduce fines and situations like that. This is where the fragmentation side of it would come in for optimization. Along with that is progressive volumes. This is a tremendous tool where, say, for example, we want to look at areas within the muck pile. We can separate that out as the mucking process is proceeding through into the muck pile. At any point, you could fly it with the drone and overlay it from the original muck pile configuration, and then be able to generate volumes for each section. And then with that, you could then take a look at the excavated volume versus your crusher throughput. And again, it just gives us another way that we can monitor and determine what kind of performance we're getting out of the blast. In this case, it was a fines project where we were looking to reduce fines and coarsen it up. In a case like this, what we would be looking for is, because we're trying to coarsen the material up, you would expect the swell of the muck pile to be increased. And of course, that's going to dramatically change the volumes going through the crusher as well. So again, it just provides another tool that we can use to track and optimize the performance of those blasts. Along with that is rock mass characterization. We can go in and characterize it, dip, strike, seams, bedding planes, things along those lines. We could also use it to assess wall damage to see if we're making improvements there, if we're making changes in the blast design. And along with that is just overall mapping. These softwares today have the capability that you could go in and fly the site, update that, and keep your mine mapping updated to the latest blast to capture that, to look at reserves and areas of that you might be looking at what kind of volumes may have in very specific areas, or how much volume's been removed out of certain areas as well. So you have the capability of mapping large areas with that. And this is where maybe the flight software would be beneficial for this type of application. But you can see how we can characterize it, and then it can be projected in a stereo net or Lambert projection, so you can see the characterization. Next, we're going to talk a little bit about the surveys and scaling the survey. One of the more popular ways today to be able to get an accurate scale is the use of ground control points. We georeference those ground control points, and doing so, we use a RTK GPS base and rover. You can see down here in the lower left picture, the base station set up on the tripod, and then the rover that we have that you can go around. And with that, we can actually go to those targets and pick up the northing, easting, and elevation of that. And then once we fly it, we can then identify each of those ground control points like you see in the image up here on the upper right, and then assign that coordinate to it. So then we can scale pretty large areas to a high degree of accuracy with this. These systems, the big advantage here is a lot of flexibility. We can just map out very specific areas that we need. We don't have to map out large areas with any kind of permanent type markers. It gives us a lot of flexibility in the field to do that, and also with follow-up analysis. The rover can also be used to go out and check and determine elevations, a whole host of things. So there's a lot of flexibility with that. We typically use the targets like you see here with the big orange dot, just because of the ease and simplicity that it gives, that we can roll it up, take it to the site, deploy it out there, pick it up later, move it around where we need it. But again, it does take some time as far as setting the targets out and of course, GPSing those targets. But again, the big advantage, especially for, say, quarry operators where they don't have permanent systems at the different locations, is they can pick this up and move it to the next site pretty easy. They can take it to construction jobs. They can use it in a whole host of ways. So it gives us a lot of flexibility. If you're not familiar with RTK, these are survey grade, what you typically see at large mine operations or construction sites. RTK stands for real-time kinematic. The way that the system works is we've got a multitude of constellations out there, the Glassnose, the US system, Galileo, there's a whole host of satellites out there. And at any point, the base station and the rover are picking up signals from multiple satellites. And then from the base station, the correction, we get that sent over to the rover by a built-in radio communication link between the two. It's pretty solid technology. A lot of these systems out there, we sell quite a few every year for this exact type application. And again, it provides a lot of flexibility and easy use out in the field with that, and can work pretty much anywhere in the world. We've used them in South America, South Africa, Europe, all over the US. So a lot of flexibility with this type of technology. The other type of scaling that can be done is what we call PPK. And this requires a special, and along with that is a PPK receiver that needs the actual drone itself. And the advantage of this type of technology is you don't have to set out multiple targets. So if you're in an area where it just isn't feasible, it's not safe, it's inaccessible, you can go in with a PPK system like this, and the tests that we've run with it, be able to go in there and georeference it again with a very high degree of accuracy, very similar to the RTK system, but without having to set out multiple targets in and around the area. Well, you can just set up the base, fly your mission, and then with the PPK, it's a post process kinematic process there, and you can see the GPS is being it's picked up by the satellite at both the base station and the drone at the same time, but it's being archived. And when you land, you just pop the card out, you download that, you download the file off of your base station, and then it is post-processed with a special software to do that. So again, the advantage with this is you don't have to deal with a lot of the targets out there. But the thing we found is more often than not, the base rover setup does probably the vast majority out there, but occasionally these situations do exist where the PPK is very helpful to accomplish the mission, even though we've got some inaccessible areas and things like that. Both of these will give us a very high degree of accuracy on our surveys. So next we're going to talk a little bit about the actual drone flights, and it's critical that we get the flight in properly. We collect the data that we need to be assured that we're going to get a good solid model out of it. But with that, we can look at what level of detail we need. If we're doing some general mapping, say we're trying to map the whole quarry, in a case like that, typically these can be done at a much higher altitude with a lower level of detail, because simply we're just trying to catch that terrain. We're not looking for any really defined characteristics of it. But with the software today, it's pretty impressive, the level of detail that you can pick up, even with some higher level, higher altitude type flights. Next is blast optimization. Here again, we want to make sure that we've got enough detail in that we're capturing, the characterization of that face and the bench. In a case like this, we don't have to get in real close. We don't need real high resolution. We can get in there and fly it, but the key thing is we need to make sure that we do capture everything we need to be able to implement a very safe design when we go in there, and that we've characterized, in this case, like you can see, more of a sawtooth face, or if we've got overhangs or cavities, it's really critical that we capture that. Next is rock mass characterization. With this, you're looking to get a much higher detail survey done with that, because we want to capture those seams in there, those joints, all the geological characterization that we need to be able to map out. So in a case like this, we're looking at probably a lower level, lower altitude, higher resolution, highly detailed flight for that, as well as with fragmentation. Again, it's what size material do we want to try to capture, and with that, we would probably fly at a much lower altitude to capture greater resolution with that. So you can see from mapping down to fragmentation, we got a lot of flexibility in that and how we want to fly it, which can save us a lot of time. In some cases, if, say, for example, general mapping, we could go in at a higher altitude flight and capture it and be able to provide adequate information for what we need for updating our quarry maps and things like that. Whereas the others, we may have to get much more and greater detail there. So to do so, we've got to make sure that the flight's done properly. And again, we've got a lot of things working against us out there: weather conditions, wind, things like that. In some cases, the flight software is helpful in doing this, or just by hand flying, as long as you can do it very orderly and be able to ensure that you're getting the capture that you need with the proper overlap of those images to be assured that we've got full coverage on the top of that bench and also on the face itself. One of the first things we want to look at is our flight track. And in this particular case, what we're looking at is our what we call ROI, our region of interest. And you can see here the boreholes. You can see the black line around it, which kind of delineates where the end of the shot is. And the fact that we need about an 80 to 90% overlap that may require us to fly outside that zone as we make our turns and come back to be able to capture it. A good rule of thumb, we want to see those points that we want in our model at least probably 5 times within the images of that particular flight. So we want to be able to go past that area of interest and come back and then capture it to make sure we've got that overlap. The other part of this is in the area of interest is, are we looking to do pre and post blast analysis? In a case like that, you can see our high wall here, and following the blast, we're going to have a muck pile that may be, in some cases, like say, for example, Corey, it could be out, 100 meters, 300 feet, somewhere in there. So in a case like this, we want to make sure that our area of interest covers where that potential muck pile could move to. So when we go out there later to capture it for post-blast analysis, to look at throw and swell and things like that, we can capture that. And then also for fragmentation as well. And if we're looking to do any type of progressive excavation and capture that to progressive volumes, we need to make sure again that that entire region of interest is in our flight. So we've got to plan that out accordingly to make sure that that area is covered. Here you can see the flight tracks, and again, altitude is very critical. The higher the altitude, AGL, above ground level, the higher the altitude, the bigger the footprint, but the lower the resolution. So when we're looking at the flight tracks, our biggest concern is to make sure we have adequate overlap. And again, what we're looking for is about an 80 to 90% overlap. It's possible to get maybe less than that, but again, the key thing here is we want to make sure that that model does not have any gaps in it. And that's where a lot of these softwares differ. Some of these GIS type ortho packages will paint over areas where there's gaps. In this type of software that's designed specifically for blasting, if it doesn't have adequate coverage from those images, it's going to leave a hole in your model. And we want this because we need to know that there's an area that's been missed, because if there's a cavity or a problem, we've got to make sure that that's flown properly and that we capture that and it's represented in there, because in a case like that, we would have to design around that. One of the key things you have to think about with your altitude is here's our bench and the floor below. And if we're looking to fly this and we're looking at the altitude that we would fly based on the floor down in front of the blast, and we look at the image and the footprint, it's going to be pretty wide, which for that particular area, we could easily get our 80, 90% coverage based on how you set your flight path up for that altitude at that, the flight path at that given altitude. Whereas if we continue to fly that up and over the bench, we're going to have a big difference in that footprint. So we need to take that into consideration. So you really want to design it, the altitude, flight altitude from the top of bench, to make sure that you've got a wide enough footprint and your flight path is tight enough that you're able to capture that 80 to 90% overlap. And of course, as you would fly out over the floor, you're automatically going to have more than enough to cover that. So these are some of the considerations you need to think about when you're planning your flights. We talked a little bit about overhanging material and cavities. To give you an idea, this cavity that you see on the right is about 20 some odd feet, so approximately 6 to 7 meters in diameter. So obviously this is a big concern in our blast design, because we need to make sure that that is characterized, it's captured, so we can implement a blast design in and around that to make sure we don't have fly rock or air blast or any kind of problems like that, and that we can load accordingly and efficiently in and around that to maintain a powder factor throughout there and not have any type of venting or problems like that. The one on the left, as you can see, a fair amount of material has fallen out. So again, big concern design-wise. So in a case like this, we have to look at how we would fly that. In a case like this, we'd want to be able to capture that crest and in 30-degree increments drop down and then capture the face as well. Depending on the height, depending on the area, again, that would determine how many flights you would take across there to capture it. But it could be that you're going to have to get down right directly in front of the face and fly parallel to it, taking your images perpendicular to that to be able to get good coverage across that face like we see here. Once we've done that, all those images can then be put in one file and processed. So what it'll do is it'll process both the orthos and the oblique images together and generate one single model out of it. But again, the consistency in your flying becomes critical. And this is where the hand flying comes in, because there's really, to my knowledge, not any one software out there that does a great job on flying across the face and at these different angles. So again, that's part of the pilot skills that you need to be able to get good solid models built from your images. So this will kind of give you an idea of what we need to do with the flights, how we go about that. If you're interested more on flights, we're going to be having a little webinar here probably in the next few weeks or month or so that you guys are more than welcome to join and learn a little bit more about that. And I'll give you the details here at the end of the program. But this will give you an idea what's involved with that, what we need to think about, and what we can capture and what analysis tools are there to go in and do an optimization program. So with that, I'll walk through a few slides on an optimization case study. This entailed a proactive, what we call proactive blast design. This is where we expose the blast face, design according to conditions, and then optimize based on verified results. And I can't emphasize that enough. You need to go in there and measure it. You need to go in there and track that to make sure we've got good data to be able to drive our decisions on this. And we found that by doing that, you can very effectively go in there and optimize and solve some major problems, and also get a blast that's very, very cost effective as well. So the tools used here, we had a drone blast optimization software, GPS, and a borehole survey system. This particular case study was at a quarry located in southeastern US. It was a 2.5 million ton a year operation. They had both rail and truck facilities there. The jaw crusher was a 50 by 62, so a 127 meter by 152, and they could take anything larger than about 48 inches or 1.22 meters was considered oversized. As far as the equipment, they had a 992K loader and 2 haul trucks, a Cat 777 and a Komatsu 785. At the time, the production was averaging about 932 short tons, so about 845 metric tons per hour through the primary. The target was to try to get up to about 1,000 or 907 metric tons per hour. So that took us into the phase 1 of the study. And again, this was the first time that this company was exposed to this technology. And so it was slowly integrated into it. But the first part of this was first identifying what was wrong. And one glance at this picture, you can see a whole host of issues. They had high wall damage, rolling floors, oversize. You can see 3 rock breakers in there. That just tells us we got a lot of issues there. But they were experiencing hard digging at the toe of the high wall and really struggling to get the performance out of it. So the goals were this. 1, they wanted to achieve a more uniform fragmentation. They wanted to increase the crusher throughput. Improve the high wall by eliminating the back break and back shatter that they were getting, because this was preconditioning the other shots. And as you'll see from some of the pictures, the walls were pretty tore up in there. They also wanted to try to get their grade control back and try to get the floor sorted out. Here you can see an example of the high wall. And again, in one glance, this tells a big story. Here you can see remnants of some half barrels there, which would indicate that maybe we've got some issues going on because they're not good burn marks like we're looking for. And then if we look at the areas on either side of this, you can see where it's just ripped and pulled this material right out, typically indicating that maybe the explosives isn't functioning like it should, because we're seeing such a varied performance all in one given area. And we would see this throughout the high wall, all over in the pit. One of the areas that we were concerned about was there were fairly significant seams. And one of the problems with that, if you don't deck through those areas or make changes in your design, the potential for transient pressures are there. And if you're not familiar with that, that's the pressures that are generated from the blast that would vent or be carried over into the next hole via seams or different avenues like that. What can occur though is we can get the misfires due to column separation, or it could affect it to the point the product will go low order or complete failure. So if we're looking at this little example here we got 3 holes. Here's a very predominant seam, let's say, running through all 3 of these holes that we've drilled through. And this is why drill logs are so absolutely critical to maintain performance, that in a case like this, if we drill through it, we load through it, and we detonate our explosive there, remember, explosives are lazy. So they're going to go to the path of least resistance. And what you can see here is all that pressure is going to vent and escape right through that seam to the adjacent hole and separate that powder column there and then the hole next to that. And again, a lot of cases, the separation could keep it away from the booster, where now we're going to have a misfire, or it could affect the product enough to cause a misfire and failure of it. And here you can see a prime example of that. And this is where I can't recommend enough video, especially with these drones. We can get a perspective on a blast we just can't get otherwise. And you can see right here all that venting going across this seam all in one area. And you'll notice it's going right back into the back rows as well. So definitely a telltale sign that these seams were important and that they needed to address that and design around it so they could prevent any kind of problems along those lines. So with that, we could go in and actually characterize that face and determine approximately where these seams were at. And then with the minimum burden profiles, go in there and look at the profiles and then determine where decking needed to be done in there to be able to prevent any issues as far as transient pressures going up through the seams. And of course, along with that, also decking for blast control as well to mitigate any kind of fly rock and air overpressures. So, some things in the very first phase came out right away that they recognized they needed to work on. And that kind of rolled in phase. And this consisted of a couple things. One was first auditing the blast pattern geometry, monitoring the drill accuracy. And again, the drill log is very, very critical part of this. And moving forward with a proactive blast design. In order to do so, they used the Blastmetrics 3D photogrammic profiling system and the advanced blast software to be able to capture and get those minimum burden designs. Along with that, they used a cabled borehole survey system to track the holes, and then an RTK, GPS, and base to then georeference. Now keep in mind, this company started off with none of this, but soon learned how important all this equipment was and ultimately being able to address these issues. And you'll see the benefits here in a little bit. We'll talk about the costs on this. So they went in, profiled multiple faces and started to compare that. The pattern was 11 by 13, about a 3.35 by 3.96 meter pattern, 127 mil hole, and the bench height was 15.2 meter, about 50 feet. So they started looking and comparing it. Along with that, they also looked at the borehole surveys, and what they found was a significant deviation in certain areas that you can see represented in here. The red lines you're seeing coming from the borehole are the actual borehole surveys integrated into the model. And you can clearly see it here on the face. You can see the bullseye view and the side views. And as we track these holes down, you can see, here you have two holes converging, and you could well imagine the problem that you would have here, because you're going to have a very high concentration of explosives in that area. But then when we look at these other holes here and over here, notice we've got a considerable distance between those. So again, dramatically affecting, the explosive distribution throughout that rock mass. And again, all of those are going to have very negative effects overall on the performance. So they certainly had a ways to go in improving their drilling, but now they have a tool in there that they could QC that and be able to resolve that and get this drilling sorted out. They also recognized significant variations in the burdens, and that the past they had burden poles and some 2D lasers and different technology that still it just was not adequate to get the burdens correct. And along with that, by introducing GPS, we now could get actual floor elevations, bench elevations, so that way we had a known elevation that you would shoot to. So it took a lot of that guesswork out that they had before, and they could really dial in exactly where they needed to be with hole depths, where the grade was at, how much subdrill needed to be on it to be able to get this right. But along with that, by doing the profiling, they were able to capture that face, characterize it, and determine exactly how much burden they had to deal with, and then they could design accordingly. Which brings us into the proactive part of this, recognizing these issues. They now saw that they had to go forward with some major changes to get this fixed. So the idea is to go in there and proactively go in there, design the blast pattern based on the high wall conditions. And I can tell you that not only there, but the other places we go, this has been the most successful way to approach this and be able to get these shots optimized and gain some good economic value out of it. And you'll see that one of the first things they realized is they had to clear that entire face of the muck, which I know is a big, big challenge for a lot of operations due to limited area, due to scheduling and just getting it coordinated. But again, when they cleared those faces out and they designed the shot according to the actual face, the improvements came very, very quickly. And when they saw toe problems or issues down there, they were able to make those adjustments, whether it's angle of hole, how they approached it, how they shot it. Again, they now had good data to be able to determine to make changes with that. They were able to adjust and correct for any all the burdens and spacings to make sure that they were dead on as far as what they were trying to implement into the field. There was no guesswork, laying tapes out and things like that. And right away, they started to see improvements in that. Significant reduction in fly rock and air blast, much more uniformity in the fragmentation right off. Along with that was making sure that the holes were drilled to depth. In some areas, they were too low. Other areas, they weren't deep enough. So now with the GPS, we've got set elevations. We know exactly where to go to do this. And that way we can get that captured, be able to get those floors flat. And again, there's other downstream values, especially with equipment, tires, things like that, teeth, the machine that aren't even rolled into to this. But the quarry originally started off with vertical holes. And as they were doing this optimization, they started to recognize that they were constantly struggling with that geology. and that the back break was pretty significant on a lot of the shots. And no matter what they tried, there still seemed to be a lot of problems. And it was very evident early on. This was some of the original blasts that they did with setback markers and burden poles and things like that. And you can see the damage that they did that from some cases being overburdened or improper burdens. You know, a whole host of things played into that. So after going in there and doing several designs, they started to determine what was the best angle for the borehole, and based on the face conditions and what they saw there, they started to make some adjustments. And ultimately, they ended up with a pattern that led them to a 12-degree angle borehole, as you can see in this design here. And this was one of the cleanup shots from one of the earlier messes. And here you can see the profile of it as they started to progress. And you can see once they started the 12-degree angled program, there were big changes in the results. They weren't constantly fighting that geology. Instead, they worked with it. And you can see here were some of the original faces. And this was during the first, or the phase 2, when they started to first lay the holes back. And here you can see where they are today with that. A huge, huge difference. And obviously there was a combination of things that made this happen, but it was a step-by-step process. And they'll tell you today that, you know, the drone technology, the blast design software, the GPS, the borehole survey systems were absolutely key into making this the success it turned out to be. Results: increased high wall stability, obviously drilling and loading much easier. We didn't have to constantly fight these faces that were a disaster. More efficient blast layout. They saw a definite increase in production and a significant decrease in the secondary breakage, where they had 3 HORAMs breakers down there running all the time. And also a reduction in loading time as well. You can see here from some of the aerial photos, you know, from early on to where they made significant changes. They had huge volumes of oversized material there for quite some time. And as they implemented that program, that went down dramatically. So just to kind of give you the overview here, pre-implementation, we were 932 short tons, 845 metric tons per hour. Post-implementation, 990 short tons, 898 metric tons per hour. So definitely a good jump there. This reduced the required time to obtain the 65,000 short tons required goal by 4.1 hours per week. So this was a big benefit as well. Here you can see the tracking on the primary crusher that they did. So they had good data to be able to justify all this and prove, you know, that these changes had made a very, very positive performance change for them, not only in the field and fragmentation wise, but when you start to look at the dollars, with an average cost on the primary, they assigned a $950 per hour cost on that crusher. That savings would relate to about $1,000+ per year. So that was a significant improvement increase there. They also tracked the secondary breakage. The first 5 months, secondary rock breakage cost around $97,000. I mean, it's expensive to run, you know, these excavators down there. So this is equated to an average saving of almost $250,000 there, $243,000 US per year. So you look at the savings that this project has gained between the two, we're up to over $440,000 per year. And I can tell you that paid for the optimization study. It pays for the equipment. You know, this was definitely a big win for them. So to kind of summarize, you know, the real success of this was a couple key things. One is a formation of an effective blast optimization team. In other words, the drillers, the blasters, quarry management, you got to have buy-in on all levels. We got to make sure everybody's pulling their weight to help aim and head towards that goal on trying to get the job done and get it done where we can show that the optimization technology will get you there by working together with that. The advanced technology was a big game changer for them on that. And going through and doing systematic changes, not doing multiple changes at one time where it's very, very difficult to tell what's helping and what's not. You try to keep it down to very small and systematic changes, tracking data and again, and verifying it to make sure that you know that you're getting good information there so you can make great logical decisions on that. So the safety and performance advantages they saw with that clearly, significant reduction in any kind of fly rock, air blast, things like that. The blast design and analysis software was really one of the big key components to this. The GPSs and the drones, again, all help them get to where they're at today with those kind of savings. So you can see how they implemented it in phases. But before we wind things up, I just want to mention that, a lot of this technology, you can start out, you don't have to get it all at once because we know there's significant cost to it, but a lot of this can be phased in. And, depending on how you want to proceed with it, what your problems are, certainly certain technology may be a good benefit for you to start. And in some cases, we've got companies that don't have GPS. They can still go out and do accurate surveys down the road. Then they can integrate in GPS. They can integrate in borehole survey systems and things like that. So, it's a great way to be able to approach this. So I hope this kind of helps shed a little light on where we're at today with this technology and a little bit of just kind of a basic overview on how you can get in there and get your mission flowing and come back with a good model and be able to generate the data and also analyze it down the road. I mentioned about we're going to have a little, it's kind of more of a workshop, a little training webinar coming up. Certainly, if you want to go to our site and sign up for the e-blast, you're welcome to do that, and we can send you a link on that when that comes about. But I guess we can open it up for questions.
Thanks for the great presentations, Mr. McClure. Now we are going to enter the question and answer section. I will proceed to mention the question asked in order to clarify the topic. The first question is, what software do you use for fragmentation? Is it accurate and automatic? And how many images per hour can be analyzed?
The fragmentation software we're using is the 3GSM fragmenter software. That's the 3D software, fragmentation software, and it really just depends on how much area you're trying to cover. If you want to just take a sample area, again, you need the 80% overlap. So I would say a typical area, you're going to probably have at least maybe 100 some images. And a case like that, you may be, it depends on what you're looking for, but you can run those fairly quick and it is automatic. You don't have to go in and like in the past where we had to outline all the different material in, in a 2D view. This is fully automated. It's capturing and recognizing the particles being 3D. And once it captures that, then that's how it generates the 3D, your size distribution that you would get from that.
The next question is, without PPK or post-process kinematic, can Datsun GPS reading be accurately input later?
Yes, it could. You could fly that, and then with the PPK, you would be post-processing that. So once you get back to the office, you would download the files from your PPK base and your PPK rover unit, and then post-process that afterwards.
Thank you. The next question is there any tool to measure the borehole depth? Do you use the drone only for case study? What is the business model of the drone service?
I think you had two questions, right? The one was borehole. For the boreholes, we use it's a gyro base survey system that we use to first survey the holes, and that also gives us the depth when we survey those holes. We found that to be really the most effective tool for that. And sorry, the second part of that was a model as far as the. I'm sorry, they asking about how to generate the model?
The question was, what is a business model of the drone service?
The drone service. Well, certainly, in a lot of cases, some companies just want to have everything done. So in a case like that, we would go in, fly it, design it, and then provide, the report on how you would load it by generating the minimum burden profiles. And that would be the report that would go to their blasters or to their service company.
Thank you. Next question is from Bill Adamson. Once the range of error in drilling results has been established and communicated, how, in your experience, have the clients gone about correcting those errors in a systematic and permanent way?
Hey, Bill, how are you? We find that once they see and identified that there's a real issue there, we find that the progressive companies out there act on it very quickly and recognize that there's a value to making these changes. But I can't tell you, there's some in the past that even though they've seen it, they just kind of keep falling back into their old ways, unfortunately. But it's good that in the last couple of years, we've seen more and more companies recognize the need to get some of these issues resolved. And once they see it in black and white, then they understand it. And in a case like this particular case study, there was no doubt the dollars were there to justify that. And, they were very hesitant to make those investments, into a permanent GPS system and things like, because quarries just typically don't do that. But once they started to see that value, they were all over it. And now it's one of those things. It's like, why didn't we do that earlier? Why didn't we invest in this? We would have saved ourselves a lot of headaches along the way.
The next question is, on slide 56, there was a view of a lot of backbreak that is strongly associated with planar discontinuities in the face.
That's, as you can see, that formation had its some pretty serious challenges. And, with some poor blasting practices, it's just going to aggravate that, as you saw there, because of the back break and back shatter was really significant in a lot of the areas. And then as we talked about in phase one, where we found that in a lot of cases, they loaded through very significant seams that we were getting these hole-to-hole pressures. That also aggravated that quite a bit. So you could see the damage that was done as compared to where they started to get the burdens right. They got that dialed in. They had the powder factor, energy ratio right. Then you started to see the fragmentation come around and the wall improved significantly, as you saw.
How were the drilling and blasting team able to blast while treating those structures more gently, therefore not loosening those blocks?
Well, a lot of it was just the problems they had in their previous designs. That's what was really aggravating it because, as I mentioned, a lot of those front row holes were way overburdened in many cases, and some were underburdened, both creating a big problem for them. But you know, if you can't get that front row moving, things start to back up, and as you can see, it has some very, very negative results because that energy, you know, it's trying to heave, it's not getting good forward lateral movement. And we end up seeing some pretty significant back break and back shatter like we did.
If we only execute a drone flight without any GPS placement, is there any another method to get the accurate coordinates?
Good question. What we've found is that to really get the accuracy, we need that GPS out there. But the other way you can do it is if you're in a situation like I mentioned early on, where you have no survey capability at all, we can set targets up with a set scale on it and fly it and capture those targets in there. And you can get a very, very accurate survey, but it will not be georeferenced. It's going to create its own local coordinates in there. And so it's possible to do that and do a good job with it. But again, what we're finding in some of these bigger operations, you know, we really need to get control on the floor. So we need to know where those elevations are at. But it's a good question because quite often, like I said, you know, some companies are looking to invest, but they can't get a GPS or they can't get survey right away. The nice thing is a lot of times, and we run into this with a lot of companies, you know, they start off with a drone and the software, and then as things progress, they can still go out and do accurate surveys. They can still do quite a bit, but ultimately down the road, then they incorporate the GPS into it, because if you want to do volumes, you really have to have GPS, and especially progressive volumes where there's changes, because we've got to have the accuracy of the georeferencing to be able to fly it a second or third or fourth time and be able to get alignment. And this is one of the things that I find out in the industry. There's companies that go out and say, oh, you don't have to worry about any kind of scaling or georeferencing or whatever. And I can tell you they're not accurate. And we've looked at that. You know, you have to have a scale in there somehow to be able to achieve the accuracy. And all it takes is one time and a bad survey, and you could end up with a problem.
Thank you. The last question is, drone as per normal operation will be able to give superficial 3D map by good photogrammic surveys that will be useful in bus planning. Can some mapping be done below the surface features as well?
Oh, for underground operations? Is that the question? Because we have done some underground flights, primarily more for rock mass characterization. That's certainly one of the next areas that we're looking at. Of course, you know, the 3GSM software originally started with rock mass characterization, hard rock tunneling, and kind of expanded from there. But now we've actually incorporated in some drone work as well.
We have another question. Do the drone is applicable to underground?
Yes, we have. Yes, we've done just limited work underground, and but it's something that we're looking at for the future as well.
Those were all the questions. Thank you very much, Mr. McClure.
Oh, thank you very much. Certainly a pleasure. And thanks everyone for joining today.
Yes, Mr. McClure. And now we are going to, uh, to end the webinar as always. Well, I am going to switch the screen, Mr. McClure.
Okay, you want me to, I can stop sharing. There you go.
Yeah, thank you, Mr. McClure. So now it is. Noé.
Okay, well, good evening to you all. My name is Noé. Now that the question and answer section is over, I would like to thank you all for having joined us today. I hope you are having a great week. This was Drone Technology to Optimize Blasting webinar. We want to give special thanks to Mr. McClure for such an amazing webinar. And thank you so much for sharing some of your knowledge with us. Also, we want to thank Mr. Watson too for supporting us in everything. Thank you so much. About our next webinar will be on June 5th, and it will be about drilling cost analysis. So we will be sending the invitation to your emails, and we'll be posting the flyer and link expression on our Facebook and LinkedIn in the next days. So please try to follow us. Okay, finally here in the ICPUC student chapter, we have this tradition to shoot fire in the hole at the end of each webinar. So please turn on your mics on the count of 3, and everyone shout fire in the hole, please. And thank you again for joining us. To hope to see you on the next webinar. Take care and be safe. So please, now you can turn on your camera, please.
Haciendo sus cámaras y sus micros, que vamos a hacer el Find the Hole. Entonces vayan encendiendo, estimados asistentes.
Okay. Please turn on your camera. Okay. Wait, share screen. Mute. Please turn on your camera.
Yeah, please.
Okay.
Noé, nos avisas.
On the countdown?
I'm gonna wait okay, a minute. So I think it's okay right now. So 3, 2, 1.
Fire in the hole.
Fire in the
Fire in the
hole.
hole.
Okay, thank you so much for us. See you. Hope to see you in the next webinar. Bye
Cheers,
bye.
everybody.
See you.
Bye-bye. Salute.
Hello, Bill. Hello,
Bye.
Terry.
Thanks.
Hi, team.
Ciao, team.
Bye,
Ciao.
Joe. Bye, Bill.
Bye-bye.
Bye.
Ciao.
Bye
See
bye.
ya.
See you.